Hello, PreCalc. We're looking at this Thursday, that's the 6th, and I am titling it partially. So we have some dramatic anticipation building, because you don't know, we're going to study permutations again, but I'm going to name it in a minute. So we'll come back and put in the full title when we are ready. So I was talking about permutations or arrangements yesterday, and we were counting. We were learning how to count them. So I want to try it again, and this time my objects are going to be 3 letters, similar to how I started yesterday with the 3 books. So let's see how it looks. I'm going to put the letter M. Let's show up. M. O1, O2. Let me see if I can get the lighting a little better. Never can figure it out. Alright, so we have these 3 letters, M, O1, and O2. So the letters in the word moo. So I could also do M, O2, O1. So that's another arrangement. So I am calling this O1 and this O2 so we can tell them apart. And then I could do O1, M, O2. I can do O1, O2, M. I can do O2, M, O1, and O2, O1, M. Alright, so there are all the arrangements of those 3 letters. And similar to ABC yesterday, 1, 2, 3, 4, 5, 6 different ways that I can arrange those, and 6 permutations. However, when you think about it though, this O and this O in real life are indistinguishable. So there really isn't a 1, sub 1, and sub 2. Like if you were to see these words in print, you couldn't tell which O was the first and which O was the second. So we're going to be more realistic and actually remove the sub 2 and sub 1s. And we see now that we have some repetitions. This is the same as this, so get rid of that one. And this is the same as that, so I'll get rid of this one, and this is the same as that. So we didn't really have 6, because some of them are repeats. We have 3. So we had quite a few less than we had originally expected. So what we call these is, when we have O1 and O2, well, when we take away the subscripts and we just have 2 letters that look alike, we say the objects are undistinguishable. So we are actually counting the distinguishable permutations. And that's what we're studying. So we will say this, making this observation and writing it, please, when objects are undistinguishable, which is another way of saying they look alike. Oops, not unlike. If they're indistinguishable, isn't it? Sorry. I need help from you guys in my English class. Indistinguishable permutations, there are fewer. So when we're saying indistinguishable, then they are alike. We can't tell them apart. So when objects are indistinguishable, there are fewer permutations, as indicated by this example, where we expect to be 6, there were really only 3. So Let's look at a formula just like yesterday when we looked at regular permutations. We had the permutations of n objects taking r at a time was going to be n factorial over n minus r factorial. So now let's do a formula for distinguishable permutations. So let's write it out. The number of distinguishable permutations of n objects with n1 of one kind n2 of one kind, etc. till we get to n sub k of one kind. When that happens, here is the formula. The number of distinguishable permutations is again n factorial, but in the denominator it's going to be different. It's going to be n factorial, n sub 1 factorial n sub 2 factorial, etc. All this in the denominator until we get n sub k factorial. So this is the number of objects that are like each other. Perhaps there's another set of objects that are like each other, and so on. So let's see how that works with the letters in the word mu. So we'll go up and do that example with this formula. Well, there were three objects, M and O, but two of them were alike. So that will be our formula. So 3 times 2 factorial over 2 factorial, we end up with 3. So let's try the letters in the word banana. So how many letters? So we're looking for the number of permutations that are distinguishable from one another. They won't be repeats. So I see 1, 2, 3, 4, 5, 6 objects, so 6 factorial. And how many are alike? Well, I see there are 3 A's. So we have 3 alike, so we'll have a 3 factorial, and I see 2 N's, so we'll have 2 alike. All right, so with that, we have 3 factorials canceled, 2 will go into 6 3 times, so we end up with 3 times 5, which is 15, times 4, which is 60. And if you're interested, your book lists all 60 of those distinguishable permutations on page 695 for your viewing amazement. All right. So that ends our topic on distinguishable permutations. Our next topic for tonight is going to look at permutations again, but we're going to branch out into a different type. So permutations order mattered. Order counts. We'll say it counts. In other words, if I have book A, B, C, if I arrange them differently, in a different order, this counts as one permutation, this counts as another. But there are scenarios where order does not count. And an example or two will help you understand that the best. For example, suppose we are going to create a committee from our class that can hire and fire teachers. And on that committee, we're going to have 3 people. So from the 11th grade, we're going to pick Shannon, Dan, and one other, Joel. All right, Shannon, Dan, and Joel. Does it really matter when I'm looking at a committee what order these are in? If I have Dan, Shannon, Joel, or Joel, Dan, Shannon, etc., does it really matter what order they're in? Is this not the same committee as this one? It is. So when we have situations where order doesn't matter, we call them no longer permutations. We call them combinations. And in those situations, the order will not count. These are the same committee no matter what order they're in. So we were counting the number of combinations similar to how we counted permutations. There should be a lot fewer combinations because all of these counted as different permutations, but they're the same combination. So there's a formula for that. And again, on this side of our line where we're in permutations, we learned the permutations of n objects taking r at a time was n factorial over n minus r factorial. And over here in combination land, it works differently. We would have, let me do the permutations. Say we have 11 in our class and we're going to take 3 people in the committee. So we learned from this formula it's going to be how many different ways could we come up with 3 people from 11, and we're saying that order did matter. So in this case it's not a committee. Say how many different arrangements of, say, seating for 3 different people from 11. So we would go 11 factorial over 11 minus 3, which is 8 factorial. So we get 990 when we multiply these numbers. So there's 990 arrangements of 11 people taking 3 at a time. But we are learning combinations now, and we expect a lot fewer. So if I'm taking a combination, this time we'll say a 3-person committee, where 3 people in different arrangements is still the same committee. So 11 objects taking 3 at a time, the formula is going to work like this. So I'll give you the general formula. We'll come up and do the specific. The combination of n objects taking r at a time is going to be n factorial, looks familiar, over n minus r factorial, looks familiar. But as I said, this is going to be a lot lower, so I'm going to add another number to divide this by, which will decrease the whole overall number, and that is r factorial. So let's count how many 3-person committees are possible from 11 people. So we're going to do 11 factorial over, I'll do it up here, 11 factorial over 11 minus 3, or 8 factorial, followed by r factorial. This is my n, this is my r. So now what happens? So we have 11, 10, 9, 8 factorial again, over 8 factorial. But we're dividing by that additional 3 factorial, which is 3 times 2. So we can take 3 into 9, it goes 3 times, 2 into 10 goes 5 times. 11 times 5 times 3 is 165. So you can see quite a bit lower in combinations than permutations. Alright, I'm not sure how many minutes I've talked. I just want to do 2 examples of combinations and call it an evening. So I'll start that on part 2.